Hi, I'm Dr. T. Welcome to my office. Today I'd like to talk a little bit about hemoglobin. It provides a nice case study into how proteins, specifically enzymes, function, even though hemoglobin is not itself an enzyme. Because it's a transport molecule, it does a lot of the kind of initial steps for an enzyme. It just doesn't do any chemistry to it. Okay, so hemoglobin is a protein. It's obviously what's found in your red blood cells. Like a lot of proteins, it does use cofactors. Specifically, it has a prosthetic group, heme, which itself holds an iron ion. The iron is then what actually directly attaches itself to the oxygen. Now, there are, of course, a whole lot of amino acids, and the orientation of those does facilitate how well it can bind the oxygen. So let's look at a little bit of what controls what's going on and kind of its goals. Now, keep in mind, the role of hemoglobin is to transport oxygen. So it needs to go into the lungs. Obviously, it's being squished around by your heart and whatnot. As it goes in the lungs, it's in an oxygen-rich environment. There, the hemoglobin needs to pick up oxygen. The hemoglobin really isn't transporting carbon dioxide. It will occasionally have one that kind of tags along for the ride, but that's more into its regulation that we'll get to here in a little bit. The carbon dioxide is dissolved in the bloodstream in the form of carbonates and bicarbonates, specifically bicarbonates, and thus is exhaled from there. That said, the hemoglobin picks up an oxygen, it's squished throughout the body, and whenever it is in a particular tissue that is of low oxygen, it releases that oxygen. So for starters, we want our hemoglobin to be able to both pick up and receive. Now, a counterpart to hemoglobin is myoglobin. Myoglobin is quite often found in muscles. It is the red in red meat. And with this one, it is storing oxygen for that muscle's use right up until the oxygen gets used. So it doesn't really need to release. It just needs to pick up. So myoglobin is a single protein. It doesn't have quaternary structure. It looks very similar to hemoglobin, but it simply grabs. And if you look at a plot of pressure of oxygen versus percent myoglobin saturation, basically how much of it got the oxygen, basically the pressure of oxygen matters some, but not a lot. It just grabs it. Now, if you look at hemoglobin, obviously it has to both take and receive. Take and give. That's the word. So its graph doesn't look like this. It's actually an interesting shape that's called a sigmoidal curve, something you actually see a lot of in biochemistry. So at low partial pressures of oxygen, which means low concentration of oxygen, it's probably in a tissue when it wants to give up its oxygen. You know, it's kind of like the UPS driver. When he's at your house, you know, the UPS driver needs to give you the package. If they don't, well, that's a problem. So, at low partial pressure, it wants to be able to give up the oxygen. And for that, what it will do is it shifts itself into a tight configuration. As it's giving up the oxygen, it rearranges the amino acids, and it packs in a little bit tighter, a little bit more rigid. Now, hemoglobin has a quaternary structure. So once one of them does that, then the other subunits, in which case there happens to be 4 of them, will also switch over and become more pulled into that tight configuration. Therefore, they will give up their oxygen. This causes hemoglobin's curve to be very low to start with. Now, as your hemoglobin gets shuffled back into the lungs, it's in an oxygen-rich environment. The partial pressure of oxygen is much higher, and it picks up oxygen. As it picks up oxygen, especially when the first couple kind of weasel their way on because there's a lot of oxygen here, then the subunits will then shift into what we call a relaxed state. And by doing so, they're much more willing to pick up and hold oxygen. This is why the back end of that curve looks, once again, nice and steep, because it is trying to, at high oxygen concentrations, bind the oxygen. Okay, now a lot of our regulation for hemoglobin is going to be adjusting this curve. First one we can look at is isozymes. So if you imagine a woman who is carrying a child, she is going to inhale oxygen. The oxygen is going to go into her lungs, go through, attach itself to hemoglobin. It's going to squash around. It'll go to the placenta where it needs to get picked up and transferred to the growing child's bloodstream. For this reason, there is a different form of hemoglobin. There's actually several forms of hemoglobin, but we're only going to look at 2. This is called fetal hemoglobin, and in this case, this particular hemoglobin has a stronger affinity for oxygen. because it needs to pull it away from the mother's hemoglobin. And that way, the growing child is able to acquire its mother's hemoglobin, or its mother's oxygen. It doesn't share the hemoglobin. Okay, a tiny amount, but not enough to count. Okay, so that's one way of controlling. We can use similar proteins, different versions of the proteins, what in enzymes we would call isozymes, in order to, differing circumstances. Now, let's look at how we can fine-tune this. Hemoglobin can be made more grabby by emphasizing and stabilizing the relaxed state, or it can be made less grabby and more givey by stabilizing the tight state. When we look at pH, this is one way of controlling it. With lower pHs, hemoglobin is more emphasis towards the tight and giving up the oxygen. This is conceptually makes great sense because when you have a low pH, what are you getting? You're getting carbon dioxide. The pH in tissues is a little bit, not much, but a little bit lower than that in the lungs, because in the lungs, the carbon dioxide is going away. Remember, carbon dioxide, when dissolved in water, forms carbonates, or actually it forms carbonic acid, which gives up H+, thus leading to a carbonate. So, as the carbon dioxide is evolving off in your lungs, then the pH is going to raise. Okay, that way, high pH, pick up the oxygen because I'm probably in the lungs. Low pH, give off the oxygen because I'm probably in the tissues. Now, one other issue that we might have. The lungs have a partial pressure of oxygen that's dependent on whatever the atmosphere is. Remember, you breathe. You take the air from inside your lungs and you go and you get rid of it. And then you suck in more air from outside. And presumably it's not the same air, otherwise you've got a problem. Well, the partial pressure of oxygen will go down if you go up in altitude. The percentage of oxygen in the atmosphere hasn't changed, but the total pressure has, and therefore the partial pressure of the oxygen is now lower. If you're familiar with dealing with altitudes, you have to acclimate to the altitude. Now, that acclimation is in no small part dealing with adjusting your hemoglobin. You have a hormone, 1,2-bisphosphoglyceric acid, that is an allosteric regulator for hemoglobin. When BPG binds to the hemoglobin, it actually makes it less able to attach oxygens. It's going to stabilize the tight form a little bit more. Now, as you go up in altitude and as you acclimate to that, you're going to produce more BPG. Like, wait, why would you want to bind less oxygen? Because of the way it shifts the curve. While you're binding and thus moving less total oxygen, the shifting and the stabilization of the tight form allows you to give off a higher percentage of the oxygen that you have then acquired. This way, while you're moving around less actual oxygen atoms, you are more efficiently delivering them to your tissues. At lower altitudes, you drop the amount of BPG and therefore move, with kind of the normal binding pattern. Additionally, the hemoglobin will do other things such as respond to the presence of carbon dioxide when it is picking up and depositing its oxygen. More carbon dioxide, the more willing it is to deposit the oxygen. Now, when it comes to hemoglobin, there are inhibitors. Two of them I want to bring up. First is carbon monoxide. Carbon monoxide is structurally similar to oxygen, although the angles in which the carbon monoxide would bind to the iron, in what's known as a ligand bond, are slightly different than that of oxygen's. Hemoglobin has a very strategically placed amino acid, so that if the carbon monoxide tries to bind, it doesn't have a particularly good angle to do so, and therefore will bind. The carbon monoxide will not bind as tightly as it would normally do so. This is actually good. The binding of carbon monoxide to iron is strong enough that if it wasn't for this position of the amino acid, it would essentially be out of equilibrium. It would be a one-way reaction. That carbon monoxide would have then bound to the iron, and the hemoglobin would have to be recycled. Thankfully, that's not the case. It's still quite sticky, but it's still in equilibrium, so carbon monoxide will eventually, specifically if you have the help of increasing the amount of oxygen and Le Chateliering it off, eventually leave the hemoglobin. Now, that is not the case for a slightly different variant. Take carbon monoxide, swap out that oxygen for a nitrogen, and you have yourself cyanide. In this case, cyanide likes to bind to iron, although a lot tighter than carbon monoxide does. And once it binds, it doesn't come off. So cyanide will bind to hemoglobin as well as quite a few other iron-containing enzymes. And once it binds, those simply have to be recycled. You can no longer function with those particular enzymes. Now, you're thinking, don't I need hemoglobin? Yeah, you do. That's why cyanide is, shall we say, toxic. Because it binds those and inactivates them. This is an irreversible inhibitor for hemoglobin, as well as actually several other enzymes that utilize iron. So with that said, I hope this gives you a brief overview of hemoglobin and ways in which allosteric regulation, competitive, and irreversible inhibitors do affect proteins and as well as enzymes within our body, even though, once again, hemoglobin isn't technically an enzyme because it doesn't actually do chemistry. It simply moves stuff. So with that all said, I'll see you next time.